I've seen a lot of people asking about gyro sync, and specifically now that Betaflight supports 2 kilohertz gyro sync, what's the deal with 2 kilohertz? Why do I want 2 kilohertz versus 1 kilohertz? So I'm going to do a little primer for you about gyro sync and the sampling rates and why the increased sampling rates are good, and actually also what's potentially bad about them. And I'm going to do that via the time-honored medium of PowerPoint slides with bullets on them. So yeah, that's what you get here, the high production values. Let's get into it. So the gyro is the sensor on the flight control board that feeds inertial data into the PID loop. The gyro tells the PID loop the copter is pitching forward, pitching back, rolling left, rolling right, yawing left, yawing right. And the PID loop then takes that data and decides what to tell the motors to do to affect a desired change in that data, right? And so that's basically how the copter flies. The gyro feeds inertial data to the PID loop. The PID loop processes that data and outputs instructions to the motors, okay? The gyro runs internally at 8 kilohertz, 8,000 samples per second. But that's too much data to pass over the I2C interface between the gyro and the processor. Boards that use the SPI interface for the gyro don't have that problem, and they can actually have enough bandwidth between the gyro and the processor to handle the whole 8 kilohertz. But then you run into the issue where the processor itself can't keep up with that much data, okay? So currently, boards with the F4 processor on them are the only ones that can run at the full 8 kilohertz rate. If you think about it, 8 kilohertz is 125 microsecond loop time, plus you would need all the other time to do all the other things, not just process the PID loop, right? You would have to finish everything you needed to do in under 125 microseconds in order to run at 8 kilohertz, right? With no overhead. So only the F4 boards can do that right now, and if you want to look into the Race Flight project, that is a project that is working on implementing 8 kilohertz gyrosync on top of CleanFlight. Currently, Betaflight runs up to 2 kilohertz, and that can be done over the I2C interface that most of the boards support. There's an interesting tangent here, which is if SPI is so much faster than I2C, why don't more boards use SPI? And the reason is that the I2C interface requires 2 pins on the microprocessor, and it's a shared bus where all the devices basically use 2 pins. So you can have as many devices on the bus. You can have a compass, you can have a barometer, you can have the inertial unit, the gyro, you have whatever else you need to do. All the devices on the board can share the same 2 pins on the processor. Whereas SPI uses 2 pins for data, and then you need it's called a select pin, and you need 1 select pin for each of the peripherals that you're going to use. So if you have a barometer and a compass and an IMU and some UARTs and all this stuff, every single device you add means you have to dedicate another pin on the processor as the select pin for that device, and you quickly run out of pins on the processor. It's much more complicated to do the board mapping. And so that's why these board designers tend to use I2C. It's just a much simpler job to support the chip and support the peripherals you need to support over I2C. The only thing is I2C doesn't run as fast as SPI. That never mattered. Remember, we used to say, some people used to say, who shall remain nameless, that 3500 loop time was plenty. So who cares? What do you need 8 kilohertz from the gyro? Well, we'll see. Okay, so the gyro can be configured with a divider that causes it to drop some samples. That's known as a decimation filter, and that brings the data rate down to something that I2C can support. So for example, if we're running at 2 kilohertz gyro sync, then the gyro is running internally at 8 kilohertz, and we've got a divider of 4, which produces a 2 kilohertz output. And basically the gyro just drops 3 out of every 4 samples, just throws them away. At least that's my understanding of how it works. There are some internal details here I'm not an expert on, and some of the people who are an expert on the internals of how the IMU chip works may correct me. But that's the gist of it. Decimation causes artifacts in the data. What that means is that it looks like there are frequencies in the gyro data that aren't really there. And that matters because the PID loop's whole job is to look at the frequencies in the gyro data and decide what to tell the motors to do based on those frequencies. And if there's bogus frequencies in there, the copter will be responding to stuff that isn't really happening. So, you know, it's like a person who's on some kind of drugs and they're waving their arms in the air trying to fight off pink unicorns that aren't really there. Okay, and so this would manifest perhaps as twitches in the copter or any kind of sort of unintended motion, depending on the nature of those frequencies. Decimation artifacts are similar to, but not exactly the same as aliasing, but similar to in the way that they create artifacts. Now let's go back to our old friend Nyquist-Shannon, the Nyquist-Shannon theorem, which I will remind you, if you haven't watched my video on aliasing, which I highly recommend you watch if you're interested in this topic. Nyquist-Shannon says that the maximum frequency you can reconstruct without distortion is 1/2 your sampling rate. So with Betaflight's default 3500 loop time, we get 285 Hertz is what that converts to, which divided by 2 gives us 142 Hertz Nyquist frequency. 2000 loop time, 500 Hertz, 250 Hertz Nyquist frequency, and so on and so on. So we can see that as the loop time goes down, as the sampling rate goes up, our Nyquist frequency goes up. And that is relevant because anything above the Nyquist frequency will still show up in your data as aliasing artifacts. It doesn't just disappear. That would be great if it just disappeared. Aliasing artifacts mean that the PID loop is going to try to compensate for gyro motion that isn't actually present, which results in worse flight performance, less of a locked-in feel, worse prop wash oscillation, etc. Let's take a look at some gyro data. Here is the frequency data coming from a copter, and we can infer what the sampling rate is by looking at the max frequency that is present on the chart. And it looks like the max frequency is about 150 Hertz. I think it seems like it's about 150 Hertz. Let's not overthink it. Which means that the sampling rate here was 300 Hertz or thereabouts. Maybe this was a 3000 loop time. I don't know exactly what it might have been, but our sampling rate here was 300 Hertz. And we can see that there's here down in the, say, 20 Hertz and below range, there is a huge spike of data going off the top of the chart. And that is the actual copter motion that the PID loop, that is sort of what you're flying based on. And this other stuff here, everything up through, like right here at around 125 Hertz, that is probably a harmonic of the prop fundamental frequency, right? And then there's something down here, right? So this is all just noise and vibration that the PID loop still has to be aware of, but maybe isn't directly responding to. And some of this, by the way, may be aliasing noise from higher frequency components that are not being correctly sampled. And it's showing up in our frequency plot, but it's not really there, and it's going to confuse the PID loop. Now we get to one, and we see the max frequency is 250 Hertz. So this is a 500 Hertz sampling rate, or 2000 loop time. And don't let the fact that the noise here looks different let you infer too much. I mean, this is a different copter, so it may be more or less noisy. We can see we still have this big spike down below about 20 Hertz, and that's the data that the PID loop is really working on. We've got this spike here a little bit below 150 Hertz, and we're building, something's going on here. What is this? It's building up. There's something going on above 250 Hertz. I don't know what it is, but maybe it's showing up as aliasing noise down here at 50 Hertz. Don't do the math on that, you guys who know about aliasing. I'm just making this up for the sake of discussion. I don't know if the numbers actually work out correctly for that. But you can see here that there's something going on here at 275 and 300 Hertz. What is it? I don't know, but boy, there's a big peak in energy, and we're not seeing it because our sampling rate isn't high enough, and Nyquist-Shannon is cutting us off, but that is still showing up in our data. Now, this is the raw gyro data from 1 kilohertz is our Nyquist cutoff. That means we're sampling at 2 kilohertz. This is from 2 kilohertz. And you can see that we're seeing a lot more complete picture of the data. Now, one other thing I want you to see, so here at around 225 hertz, this is probably the main prop fundamental. That is the prop vibration frequency. We got a big spike here, and we've of course got this spike down below 20 hertz, which is the actual copter motion, right? And then we can see all this other stuff here going all the way up to 1 kilohertz. Now notice that when you get above, I guess 350 hertz, there's not a lot of noise there. It's very, very quiet. Now when you get above about 600 hertz, there's really not a lot of noise. It's really trickling off, right? So one of the things that I think we can take from this is that I expect that there will be diminishing returns from increased sampling rates. We can already see that the difference between 1 kilohertz sampling and 2 kilohertz sampling, so 1 kilohertz sampling would get us up to about 500 hertz. And we can see that above 500 hertz, there's not really very substantial signal energy. And so there's going to be some aliasing from this signal energy if we were sampling at 1 kilohertz, but it's not going to be very substantial. It's going to be relatively weak. And there's so much strong energy already in here that any aliasing artifacts from this stuff, I'm not an expert on this topic. If somebody like Boris disagrees with me, then I will defer. But it feels to me like the strength of this is so weak that it would not have a substantial effect up here. Okay, and as we go forward to 4 kilohertz and 8 kilohertz, we're not going to suddenly find, whoa, there's a giant spike at 6 kilohertz. That's just not the way this is going to work. There's nothing on the copter that's going to make noise at 6 kilohertz. In fact, the higher the frequency we go, the weaker these signals are going to get. And so I really feel like when we get to 2 kilohertz, we're certainly starting to get to the point of diminishing returns, at least looking at the spectral data and from the perspective of aliasing and so forth. Okay. So why is gyrosync good? First of all, why is gyrosync good? Forget about the sampling rate. Before we had gyrosync, we just had the loop time, right? And so the gyro was running at, say the gyro was running at 1 kilohertz and the loop was running at 2000 or 3500 or whatever it was. Those two things were completely out of sync. And whenever the loop finished running, it went to the gyro and said, give me some data. And whatever the latest data the gyro had was, the gyro just pushed it out, okay? Without gyro sync, you could set your loop time to be the same frequency as the gyro. So if the gyro is running at 1 kilohertz, you could set a 1000 loop time. And there still would be, that would be good. That would be better than like setting a 1500 loop time or a 1800 loop time, right? Because the gyro and the PID loop would be close to in sync, but they wouldn't be running at exactly the same speed because there's always a little bit of fluctuation. And so anytime you've got a timer-based situation like that, you're still going to get some distortion in the data because they're not going to be perfectly synced up. So one of the things Boris did earlier, happened a while back, is implement gyro sync, which means that instead of the loop running on a timer, the loop runs based on an interrupt. And what that means is that the loop sits there and waits. And when the gyro has data for the loop, the gyro says, hey, come get this data. And the loop goes and gets it and works on it. And then it waits. And when the gyro has more data, the loop comes and gets it and then works on it. And what that means is that they are exactly in sync at whatever rate the gyro is running at, in this case, but 1 kilohertz up through very recently. And so if the gyro is slightly fast or slightly slow with the data, that data is not going to get lost. Okay, so that's why gyrosync is good. Why is faster gyrosync good? 1 kilohertz, 2 kilohertz, 4 kilohertz, 8 kilohertz. Higher sampling frequencies increase the Nyquist limit. This results in accurate sampling of higher frequency data and reduced aliasing artifacts at lower frequencies. And again, if we go back here, we can see that the higher gyrosync is letting us look further up the frequency spectrum, right? And that's resulting in accurate sampling of this data up here, which is not too big of a deal in my opinion, because there's nothing going on at 900 hertz that affects your flight significantly. But there may be something going on at 900 hertz or 700 hertz or 600 hertz, or oh, now we're starting to see some significant noise down around 550 maybe. There's something going on there that if you didn't sample it, it would create aliasing artifacts down here that would affect your flight. Okay? Why is faster gyrosync challenging? Well, first of all, the devs now have to make intentional decisions about how to filter the incoming gyro data. Much of the new high-frequency data we're getting is not really useful for flight performance, in my opinion. Actual useful flight-related gyro data is mostly below 50 hertz, and everything else is noise that you just have to figure out how to get rid of. So when you're sampling at 500 hertz, your Nyquist theorem or your Nyquist frequency is 250 hertz, and whatever's going on above 500 hertz is, I mean, it just is what it is. You can't do anything with it. You can try and maybe pre-filter the data. You know, there's things you can try to do, but at the end of the day, you just got to kind of accept it and deal with it. So when we have these higher sampling rates, now this thing that was always a problem, but there was nothing we could do about it, so we just kind of lived with it. Now we have to decide what to do with it. And I say we, and by we I mean the devs, not the pilots. The devs have to figure out how to solve this. The main advantage of faster sampling rate is not that it gives us accurate sampling of the higher frequency data, which is not really that useful for flight anyway. I think that it's the reduction of aliasing and reduction of decimation distortion at lower frequencies. I made that up. That's my opinion. But if a dev disagrees with me, then I defer to them. Another challenge of faster gyrosync is that Blackbox data will contain lots of high-frequency components that were getting just dropped out by the Nyquist limit before. These high-frequency components do not really directly affect flight performance, and they make the Blackbox logs difficult to interpret. I think if we keep going to higher gyrosync rates, we are going to need low-pass filters in the Blackbox viewer if the gyro data isn't ultimately low-pass filtered in the flight controller first, because you just get these huge wiggly-jiggly lines, and it's really hard to see what the PIDs are really doing down at the frequencies that you really care about where flight is directly affected. And finally, faster gyrosync is challenging because the faster your loop time, the more Blackbox data you've got, and that means that OpenLog serial ports can't keep up at one-to-one. So you have to run your Blackbox rate denom at 1:3 or something, and that results in aliasing in the Blackbox data. In other words, you're going to see frequencies in the Blackbox data that isn't really present, and that makes tuning a little more difficult. This is why I think that onboard SD card readers via the SPI interface are probably, that's the only solution I can see for Blackbox logging at say 2 kilohertz, 4 kilohertz, 8 kilohertz. A serial port, a UART, is not going to be able to do it, and a data flash chip isn't big enough. It's fast enough, but it's not big enough to hold like a full day of flight time. So it seems to me like flight controllers with onboard SD card readers via the SPI interface are going to be the way to go for development and tuning in the future. There's one more reason why faster gyrosync is challenging, and that is that copters running at a faster gyrosync rates seem to fly a lot better. They do. That's what we're seeing. I'm seeing on the Betaflight thread and in the Blackbox logs that are being submitted to me. They fly a lot better, but this actually makes tuning harder because the signs of a bad tune are not as obvious. And so a copter may appear to fly perfectly well, but the motors and ESCs are overheating or even burning out because there are such huge micro oscillations. And those micro oscillations coming out of the PID loop, they wouldn't have been there if the PID loop was running slower, because these high frequency components, they would have been filtered out by the aliasing. They would have been converted to low frequency components by aliasing, and that would make your copter fly worse, but it wouldn't destroy your motors. Now that we're sampling accurately, we are actually seeing these high frequency components, and the PID loop is trying to deal with them, and the motors are freaking out and they're burning out, and the ESCs are burning out. So before 2 kilohertz gyrosync, the copter might have been unflyable. You would have tried to, your P gain's too high, your D gain's too high. You try to take off, it shakes itself, and you land and you fix it. But with 2 kilohertz gyrosync, the copter seems to fly fine, and then suddenly it falls out of the sky because you actually were burning out your ESC and you didn't know it. The other thing is that the expected P and D gains especially, I is not so much affected because I inherently has a low-pass filter in it because it's an integrator. But the P and the D gains that we expect to get are different. So you may have a copter with some P and D gains that work under 1 kilohertz, and when you go to 2 kilohertz, they're actually too high. So if you're going to 2 kilohertz, definitely, I know Boris has come up with defaults that he feels are good for most people, but my recommendation would be that anybody flying on 2 kilohertz for the first time, definitely treat it as a completely new tune and try to start with very low P and D gains, or like take off, do a 10-second flight, land, and check your motors, or more importantly, have Blackbox. I think that from at 1 kilohertz, you could still tune line of sight and with your HD cam pretty well, although it got a little challenging if you didn't know what you were doing. And with 2 kilohertz and above, from what I'm hearing from people, it seems like line of sight tuning, I mean, you could probably make it fly good, but you won't know what's going on underneath. You won't know if you've got huge P-term or D-term oscillations unless you've got Blackbox. So I really feel like Blackbox is going to be a critical part of tuning going forward as we get to higher sync rates. Although, as I suggested, I also feel like there's going to be a law of diminishing returns here. And we may find that at the higher sync rates, it makes sense to just make an informed decision about how to get rid of some of that data and say filter it down with like a low pass filter or something and get rid of some of that. Because do we need 4 kilohertz frequency components fed into the PID loop? Probably not. Okay. Okay. I hope that was helpful. And as always, happy flying.